All right, so now we're going to talk about incorporating electron pushing those curve arrows into our reactions. This is going to create what are called reaction mechanisms. This is a skill that we learned first with resonance. Now we're carrying that electron pushing skill into chemical reactions. Okay, so let's take a look at what that would look like here. So let's just remember from resonance what these electron pushing arrows are. By the electron pushing, I'm talking about these curved arrows down here. And remember, we had rules for drawing our curved arrows. The base of the arrow is going to be at a pair of electrons that are going to be pushed, right? Electron pushing arrows. What you want to think about when you're drawing these arrows is you are grabbing this pair of electrons that was at the base of that arrow, and you're moving them to the tip, okay? So in this case, what's being shown in this electron pushing is this pair of pi electrons is being pushed up onto that oxygen atom as a lone pair. The other thing that you always want to remember when we're talking about doing these electron pushings are you have to keep track of your formal charges. So in this case, when I move that pair of electrons up to that oxygen, it creates a formal charge of -1. And because of conservation of charges, I need to have the same net side on both sides of my equation. The formal charge on the carbon will be +1. Okay, so this is what we saw with electron pushing in resonance. We're going to see the same thing in chemical reactions, where we're going to be grabbing a pair of electrons with the base of our arrow and bringing those over where the tip of the arrow sits at an atom, okay? So what we're doing in chemical reactions is not just bouncing electrons around the same structure. That's what we were doing in resonance. Now, again, the basis of any chemical reaction is that bonds are being made and bonds are being broken. So that's what we're really showing with our electron pushing in a chemical reaction. So there's both of those examples here. So in this case, this arrow in orange, that are colored in orange, is a bond being formed, bond forming. All right, so this is the bond that's being formed between my base and the proton, right? A base is accepting that proton. So that's this bond that's being formed here. This bond, this set of arrows here is this pair of electrons that was in that covalent hydrogen-oxygen bond is now being taken and jumped onto the oxygen atom. So this is a bond breaking. All right, so the bond that was being formed, it started at a lone pair and attacked an atom. And that forms a new bond between that, in this case, oxygen and hydrogen. The bond being broken, the base starts at a bond and then jumps onto an atom. Okay, so there's two different things happening here. One is bond formation and one is bond breaking. And so just to keep track of these electrons that were being pushed, this pair of electrons on my conjugate base used to be in my acid before that bond broke. And likewise, this orange arrow there would represent one. I guess let me do this, see how quick. Represents this new oxygen-hydrogen bond. All right, and then all the same rules that we learned about before still apply. Notice that the net charge on my base has gone +1 to my conjugate acid, and the net charge on my acid is -1 to my conjugate base, right? So we got to make sure that we're keeping track of our charges. Okay, the acid, one thing that's important to note about acid-base reactions is the base is accepting the proton in the same step that the acid is donating the proton. So both of these arrows are needed at the same time, representing the fact that these two occur simultaneously. All right, so now we're going to draw our own reaction mechanism here. Well, we've already been told what's playing the role of the acid and what's playing the role of the base. So then we just got to remember, well, what does it mean to be an acid? That means that the acid is going to lose a proton. So we'll lose this guy here, and the base is going to be the one accepting that proton. But now we got to be able to represent this with our curved electron pushing arrows. The new bond that's going to be formed is going to be between the lone pair on my base and that proton, right? So this arrow, you could think about your base as attacking your acid. And then that will happen simultaneously with that bond being broken in the acid, that hydrogen and whatever the other thing is bond in the acid, right? Because my acid is donating my proton. Okay, so then if I'm going to draw my conjugate acid and conjugate base here, I have to draw my base has now accepted that proton. I'm going to keep it colored in red here so we can keep track of what's what. And then remember, I have to add 1 to the formal charge of whatever it is in that base that accepted that proton. Likewise, in this case here, if we're following this arrow here, this is the bond breaking between hydrogen and oxygen is getting that pair of electrons that was formerly in that covalent bond. So in this case, becoming a hydroxide ion. All right, so let's make sure that we can label our conjugate acid and conjugate base. That's an important part. This is the base after it's accepted the proton, so it's my conjugate acid. And this is the acid after it's lost its proton, so it's the conjugate base. Okay, so now let's see if we can follow an even more complicated reaction mechanism using these curved electron pushing arrows. So this is no longer going to be just an acid-base reaction. It's actually going to be what's called an elimination reaction. We won't cover this for a few chapters, but nonetheless, I just want to make sure that we can follow what's going on with these electron pushing arrows. So don't worry about why this reaction is occurring. Just make sure you can follow along with what bonds are being broken and what bonds are being formed. Okay. So actually, I want everybody to take a second and pause the video and give me what the product of this first step would be here. Okay. Most important to note is, again, what bonds are being broken, what bonds are being formed. This arrow right here would represent the formation of a new bond. It's starting at a lone pair and reaching over to an atom. So this is bond formation. And likewise over here, or in contrast over here, we have an arrow that's starting at a bond and ending at an atom. So this is a bond that's breaking. All right, so if I'm going to draw the products of this reaction, what I'm going to do is sort of just copy what's already there. But now I'm going to draw in that new bond that's been formed. So in this case, it's between an oxygen and a hydrogen. And likewise over here, I can just think about it as I need to get rid of this bond here. So what I'm going to be left with is, I guess I'll draw it the same. But now that bond has been broken and is a lone pair. The other thing you got to make sure to do is pay attention to charges. I have an oxygen that has 3 bonds and 1 lone pair. So this needs a positive charge. You'll get really good at being able to tell when something's going to get a positive charge and a negative charge. It's just something to be mindful about because it is one of the more difficult parts of drawing reaction mechanisms. Okay, so here's the product of the first step. This first step actually is an acid-base reaction, but we're going to see a few steps after this that aren't. Okay, so now that we followed this one, whoops. What's happening here? Everybody take a second and draw me what the product of this step is going to be. Notice I only have 1 arrow here, so is a bond being made or is a bond being broken? In this case, we actually have a bond being broken. It's starting at a bond and it's ending on an atom. So this is a bond that's going to be broken. If I'm going to draw my resulting molecule, again, going to just kind of copy what I have down. But now I'm not going to draw in that one bond that was broken. And this would be, the other atom that would be created would be water. And now am I done? Hopefully you've caught the fact that I have not properly included all of my charges. This carbon here at the center, it used to have this pair of electrons associated with it. Well, that got snatched away and it's now on that oxygen. So I have a positive charge on that carbon. Again, conservation of charges at every step, because I started with a positively charged species at the first step, at every step along the way, I should have at least one positively charged species. Okay, so now I'm left with this carbocation, so let's see what happens next. And again, the whole goal isn't to understand why, but just to make sure that we can follow what's going on with these arrows. Okay, so now in this step, I have this carbocation. Notice that what's happened here is, as I had drawn it, it was just like this. What they did was explicitly to draw in that one hydrogen bond, just one of those hydrogen bonds that are rather carbon-hydrogen bonds that were implicit in my bond line structure. It was drawn explicitly here because that pair of electrons is going to come into play. So now everybody take a second and see if you can't give me the product of this reaction here. What bonds are being broken and what bonds are being formed. Okay. So here we have a bond that's being formed when water comes and grabs this hydrogen. And this now is a bond that's breaking. This is why I don't really like the book's notation. I would have put it over here. But this is actually something that's a little bit different than what we've seen before, in that this pair of electrons is coming down, is breaking in this bond, or rather, how do I say this? This bond right here is breaking as that hydrogen's being grabbed. But now that pair of electrons is coming down and forming a new bond with this carbon, with that carbocation. Okay, so the pair of electrons that was being shared between carbon and hydrogen are now being shared between carbon and that carbocation. And so that's creating a double bond right there, right? Again, this pair of electrons here used to be in this carbon-hydrogen bond. Oops. Okay, so these, you could see why these electron pushing arrows are going to be so important. They show you exactly what's happening in a chemical reaction. What species is reacting with what? One of the things I told you this first week is that one of the patterns we're going to see over and over again in organic chemistry is you have electron-rich species reacting with electron-poor species. It's the same thing in your acid-base chemistry as well. You have this electron-rich base, right? So focusing on this step here, which is an acid-base step. You have an electron-rich base, and its electrons are reaching out and grabbing this electron-deficient proton, right? That proton is, it's electron-deficient, in this case because it's bound to this positively charged oxygen. That's a pattern we'll see with all of our acids.